of my Advent of Code series. I think last Saturday's problem was pretty difficult. So let's see how this Saturday's problem is. All right. Traps and safe tiles. Tiles are arranged in rows. They're all the same width. Okay. All right. The type of tile is based on the, okay. All right. Let's see. For example, suppose you know the first row with tiles marked as letters and want to determine the next one. The type of tile in each row is based on the types, and to either side. Okay, got it. So it's kind of like Game of Life. Okay, if either side it counts as. All right. Suppose you want to know. Okay, is based on the types of tiles A, B, and C. Got it. Okay. Let's call 3 tiles left, center, and right. Okay. Thus, then A is a trap if only in one of the following situations. Only in one of the following situations. Okay, so it's any of these. Okay, so I think. All right. So maybe what we need is define trap, and then we'll have A, B, C like this for left, right, and center. So, okay, so, all right. Starting with, you can determine the next row. Non-existent means safe. Okay. Got it. Got it. Okay, get your puzzle input here. Okay. So I guess, so we'll use dots and carrots here. So let's see. If any of these are the case. So I guess so I think this is trap, right? Okay, so the first case here is that, and then the right tile is not a trap. Okay, and then that's case 1. Case 2, center and right are traps, but the left tile is not. Case 3, only the left is a trap. This. Or case 4, only the right is a trap. Like this. All right, so then let's see. So the starting state is going to be, okay, so we're going to take 40 rows, or the starting state we know is this string. All right, then we'll define next row of row to be, all right, now how do I need to do this? I think that I need to like put safe tiles on both sides of row, break it up like that, and map, let's see, so map like if okay, so map trap should be fine. Then map true looks like this, and false looks like this. And apply stir to this. Okay, let's test this. What is the next row here? All right. Okay, and then I need to fix this somehow. I think I need to clip these last two things off. So I think I need to take count row like this. All right, and then let's do take 3, iterate next row on this. Like it. Okay, so let's take 40, iterate next row on starting state. Concatenate all these together. Filter by it's got to match, so they're asking for how many safe tiles there are. All right, and then count it. 1956. Right answer, right, 11. Back to day 18. How many safe tiles are there in a total of 400,000 rows? All right. And I glance at this quickly here to see if we can optimize it, and I think we can. So let's use a little, is a loop okay? So start with this, that's good. Taking 400,000, that's still good. Apply concat is gonna be wrong. I think better to, actually no, because it's still lazy. Yeah. I think I like this just fine. Okay, let's kick this off here. Let's see, calling a function 400,000 times seems like it should be pretty quick. I'll keep my eye on this, but then also see if there's a way to do it faster. Let's see. I could map. I could map this filter here to the individual elements. Like this. It's still asking for safe tiles, right? Then like map count and then apply plus. Would this be any faster? Also sounds like we're getting some music here. Pause that. Right, let's take a look. This is still going. Will this be faster? Not sure. Let's just try. So this will run on a different thread, so I don't think I'm losing any compute here. Try this. This does seem like it's going to be working off of, because, yeah, maybe it seems like fewer, I don't know, maybe fewer additions will happen. So waiting for this to return here, waiting for this to return here. Yeah, it'd be nice to get some update on the current state, but I guess we can just be patient at 400,000. I mean, I gotta think that we're gonna be pretty good. I think let's see. I think I can start another REPL to the same closure environment. Yeah. So maybe what I can do is sort of just time this for a much smaller n. So let's say just taking 400. Okay, 4,000. This should be pretty linear. Okay, so it's saying that it's taking 3 seconds to do 4,000. All right, and then I guess let's just compare to this implementation up here. Basically the same amount. So if it's taking 3 seconds to do 4,000, then to do 400,000, it's going to take 300 seconds, 5 minutes. Not a huge. I mean, I wish it could be better. There is probably a better multi-threaded way to compute something like this, but I think it's that this has already been running for a little while, and we should be pretty close. Let's see other ways to optimize. Yeah, rather than computing, I guess maybe like we could represent. Maybe it's some kind of we like represent each. Oh, there we go. All right. Right answer, 48th. Yeah. So once again, getting a pretty quick initial answer and then a pretty slow second answer. I think actually, I think what would make something an approach like this actually run faster would be using transducers, because what is essentially happening is that we're making like a lot of cons cells, ephemeral garbage that needs to be collected, and objects need to be instantiated. And yeah, generally when performance doesn't matter, you can just sort of ignore that stuff. But I think we're seeing the difference between rank 11 and rank 48 today. So that means that 37 people not only solved our part one of the problem, but then they also went ahead and solved part two. Like they caught up to us. So that might be worth thinking about for a future video. But yeah, let's go over the problem real quick here. Here we go. So yeah, so this reminds me of Game of Life, or I guess it's like sort of like a one-dimensional version of Game of Life, where there are your representation of your state is a line where tiles are either safe or traps, and then at each step along the way, the position of the trappiness of a tile is going to be based on the previous tile and its neighbors. So our logic is encoded up here. We see something as a trap if it follows any of these rules. These rules are pretty easy to translate into just binary Boolean logic here. And then to get the next row of things, what we have to do is, because tiles off the end are defined to be safe, we'll just put a couple of safe tiles on either side of the row, break it up into 3 chunks at a time, find out if it's a trap, and then we're just sort of returning the caret symbol or the dot, depending on whether it is. And then this I had to throw in because by adding these two dots on either side, we're producing just a little bit more output than we actually need, and then reconstitute into a string again. So yeah, to talk about the sort of the slowness of the program, again, this could be written to be a lot faster. However, in practice, in these sorts of things, often unless you can make those optimizations in your first pass, then oftentimes it just makes more sense to let the computer crank on the problem, and then move on to like the next thing that you have to do for thinking. So it's sort of the computer's good at calculating and you're good at writing code, so don't worry about it too much. And then yeah, then the roll up, pretty straightforward stuff. We're just calling the iterate function, and then it helpfully tells us that we can use the first row of input, and then yeah, we just take 40 of them here, and this gives us our first answer, and then for the next answer, just 400,000. So Yeah, so was glad to get some points for the day. Let's see what this does to our leaderboard. Position. Tied for 63rd. All right, not too bad, not too bad. And let's take a look at the advent calendar. Yeah, very nice, very nice. Yeah, still not totally sure what kind of thing this is with the blue lights. But the city's looking great. Yeah, it's starting to really light up, and looking forward to tomorrow's problem. Thanks for watching.